In linear algebra, a rotation matrix is a matrix that is used to perform a rotation in Euclidean space. For example, the matrix rotates points in the xy-Cartesian plane counterclockwise through an angle theta about the origin of the Cartesian coordinate system. To perform the rotation using a rotation matrix R, the position of each point must be represented by a column vector V, containing the coordinates of the point. A rotated vector is obtained by using the matrix multiplication RV. Rotation matrices also provide a means of numerically representing an arbitrary rotation of the axis about the origin, without appealing to angular specification. These coordinate rotations are a natural way to express the orientation of a camera, or the attitude of a spacecraft, relative to a reference axis set. Once an observational platform's local xyz axes are expressed numerically as three-direction vectors in world coordinates, they together comprise the columns of the rotation matrix R that transforms directions into equivalent directions expressed in platform local coordinates. The examples in this article apply to active rotations of vectors counterclockwise in a right-handed coordinate system by pre-multiplication. If any one of these is changed, then the inverse of the example matrix should be used, which coincides precisely with its transpose. Since matrix multiplication has no effect on the zero vector, rotation matrices can only be used to describe rotations about the origin of the coordinate system. Rotation matrices provide an algebraic description of such rotations, and are used extensively for computations in geometry, physics, and computer graphics. Rotation matrices are square matrices, with real entries. More specifically, they can be characterized as orthogonal matrices with determinant 1, that is, a square matrix R is a rotation matrix if RT equals R-1 and det R equals 1. In some literature, the term rotation is generalized to include improper rotations, characterized by orthogonal matrices with determinant -1. These combine proper rotations with reflections. In other cases, where reflections are not being considered, the label proper may be dropped. This convention is followed in this article. The set of all orthogonal matrices of size n with determinant +1 forms a group known as the special orthogonal group SO. The most important special case is that of the rotation group SO. The set of all orthogonal matrices of size n with determinant +1 or -1 forms the orthogonal group O. In two dimensions, every rotation matrix has the following form. This rotates column vectors by means of the following matrix multiplication. So the coordinates of the point after rotation are. The direction of vector rotation is counterclockwise if theta is positive, and clockwise if theta is negative. Thus the clockwise rotation matrix is found as. Note that the two-dimensional case is the only non-trivial case where the rotation matrices group is commutative, so that it does not matter in which order multiple rotations are performed. An alternative convention uses rotating axes, and the above matrices also represent a rotation of the axis clockwise through an angle theta. Non-standard orientation of the coordinate system. If a standard right-handed Cartesian coordinate system is used, with the x-axis to the right and the y-axis up, the rotation R is counterclockwise. If a left-handed Cartesian coordinate system is used, with x directed to the right but y directed down, R is clockwise. Such non-standard orientations are rarely used in mathematics but are common in 2D computer graphics, which often have the origin in the top left corner and the y-axis down the screen or page. See below for other alternative conventions which may change the sense of the rotation produced by a rotation matrix. Common rotations particularly useful are the matrices for 90 degrees, 180 degrees, and 270 degrees rotations, in 3 dimensions. Basic rotations. A basic rotation is a rotation about one of the axes of a coordinate system. The following three basic rotation matrices rotate vectors by an angle theta about the x, y, or z axis, in 3 dimensions, using the right-hand rule, which codifies their alternating signs. For column vectors, each of these basic vector rotations appears counterclockwise when the axis about which they occur points toward the observer. The coordinate system is right-handed, and the angle theta is positive. Rz, for instance, would rotate towards the y-axis a vector aligned with the x-axis, as can easily be checked by operating with Rz on the vector. This is similar to the rotation produced by the above-mentioned 2D rotation matrix. See below for alternative conventions, which may apparently or actually invert the sense of the rotation produced by these matrices. General rotations. Other rotation matrices can be obtained from these 3 using matrix multiplication. For example, the product represents a rotation whose yaw, pitch, and roll angles are alpha, beta and gamma, respectively. More formally, it is an intrinsic rotation whose Tate-Bryan angles are alpha, beta, gamma, about axes z, y, x respectively. Similarly, the product represents an extrinsic rotation whose Euler angles are alpha, beta, gamma about axes z, y, x. These matrices produce the desired effect only if they are used to pre-multiply column vectors. Conversion from into axis angle. Every rotation in 3 dimensions is defined by its axis, a direction that is left fixed by the rotation, and its angle, the amount of rotation about that axis. There are several methods to compute an axis and an angle from a rotation matrix. Here, we only describe the method based on the computation of the eigenvectors and eigenvalues of the rotation matrix. It is also possible to use the trace of the rotation matrix. Determining the axis given a 3 times 3 rotation matrix R. A vector u parallel to the rotation axis must satisfy, since the rotation of u around the rotation axis must result in u. The equation above may be solved for u which is unique up to a scalar factor unless r equals I. Further, the equation may be rewritten which shows that u lies in the null space of r minus I. Viewed in another way, u is an eigenvector of r corresponding to the eigenvalue lambda equals 1. Every rotation matrix must have this eigenvalue, the other 2 eigenvalues being complex conjugates of each other. It follows that a general rotation matrix in 3 dimensions has, up to a multiplicative constant, only one real eigenvector. Determining the angle. To find the angle of a rotation, once the axis of the rotation is known, select a vector v perpendicular to the axis. Then the angle of the rotation is the angle between v and rv. A more direct method, however, is to simply calculate the trace, i.e., the sum of the diagonal elements of the rotation matrix. Care should be taken to select the right sign for the angle theta to match the chosen axis. Rotation matrix from axis and angle. For some applications, it is helpful to be able to make a rotation with a given axis. Given a unit vector u equals, where ux2 plus uy2 plus uz2 equals 1, the matrix for a rotation by an angle of theta about an axis in the direction of u is. This can be written more concisely as where is the cross product matrix of u, is the tensor product, and I is the identity matrix. This is a matrix form of Rodriguez rotation formula, with if the 3D space is right-handed, this rotation will be counterclockwise when u points towards the observer. Rotations in the counterclockwise direction are considered positive rotations. Note the striking, merely apparent differences to the equivalent Lie algebraic formulation below. #exponential map. Properties of a rotation matrix. For any rotation matrix R acting on n, It follows that a rotation is termed proper if and improper if. For even dimensions, the eigenvalues of a rotation matrix occur as pairs of complex conjugates which are roots of unity and may be written. Therefore, there may be no set of vectors which are unaffected by the rotation, and thus no axis of rotation. If there are any real eigenvalues, they will equal unity and will occur in pairs, and the axis of rotation will be an even-dimensional subspace of the whole space. For odd dimensions, there will be an odd number of such eigenvalues, with at least one eigenvalue being unity, and the axis of rotation will be an odd-dimensional subspace of the whole space. For example, in 2 space, there are either 2 complex eigenvalues or 2 real eigenvalues equal to unity. In the case of the 2 unit eigenvalues, the rotation is a null rotation, but otherwise, there is no axis of rotation. In 3 space, there will be an axis of rotation or the rotation will be null. In 4 space, there may be no axis of rotation, or there may be a 2-dimensional axis, a plane through the origin, called the axis plane. As always, when all eigenvalues are unity, the rotation is a null rotation. The trace of a rotation matrix will be equal to the sum of its eigenvalues. For n equals 2, the 2 eigenvalues are and the trace will be where is the rotation angle about the origin. For n equals 3, the 3 eigenvalues are 1 and where is the rotation angle about the axis line. The trace will be. For n equals 4, the 4 eigenvalues are of the form and the trace will be. If one of the angles, say, is equal to 0, then the rotation will be a simple rotation, with 2 unit eigenvalues and the other angle. The eigenvalues will be repeated twice, and every vector from the origin will be rotated through the angle. The trace will be. Examples. Geometry. In Euclidean geometry, a rotation is an example of an isometry, a transformation that moves points without changing the distances between them. Rotations are distinguished from other isometries by 2 additional properties. They leave one point fixed, and they leave handedness unchanged. By contrast, a translation moves every point, a reflection exchanges left and right-handed ordering, and a glide reflection does both. A rotation that does not leave handedness unchanged is an improper rotation or a roto-inversion. If a fixed point is taken as the origin of a Cartesian coordinate system, then every point can be given coordinates as a displacement from the origin. Thus one may work with the vector space of displacements instead of the points themselves. Now suppose the coordinates of the vector p from the origin, O, to point P. Choose an orthonormal basis for our coordinates, then the squared distance to P, by Pythagoras, is which can be computed using the matrix multiplication. A geometric rotation transforms lines to lines, and preserves ratios of distances between points. From these properties it can be shown that a rotation is a linear transformation of the vectors, and thus can be written in matrix form, QP. The fact that a rotation preserves, not just ratios, but distances themselves, is stated as or because this equation holds for all vectors. P. One concludes that every rotation matrix, Q, satisfies the orthogonality condition. Rotations preserve handedness because they cannot change the ordering of the axes, which implies the special matrix condition. Equally important, it can be shown that any matrix satisfying these 2 conditions acts as a rotation. Multiplication. The inverse of a rotation matrix is its transpose, which is also a rotation matrix. The product of 2 rotation matrices is a rotation matrix. For n greater than 2, multiplication of n times n rotation matrices is not commutative. Noting that any identity matrix is a rotation matrix, and that matrix multiplication is associative, we may summarize all these properties by saying that the n times n rotation matrices form a group, which for n greater than 2 is non-abelian, called a special orthogonal group, and denoted by sun, or sun. The group of n times n rotation matrices is isomorphic to the group of rotations in an n-dimensional space. This means that multiplication of rotation matrices corresponds to composition of rotations, applied in left to right order of their corresponding matrices. Ambiguities. The interpretation of a rotation matrix can be subject to many ambiguities. In most cases, the effect of the ambiguity is equivalent to the effect of a rotation matrix inversion, alias or alibi transformation. The coordinates of a point P may change due to either a rotation of the coordinate system CS, or a rotation of the point P. In the latter case, the rotation of P also produces a rotation of the vector V representing P. In other words, either P and V are fixed while CS rotates, or CS is fixed while P and V rotate. Any given rotation can be legitimately described both ways, as vectors and coordinate systems actually rotate with respect to each other, about the same axis but in opposite directions. Throughout this article, we chose the alibi approach to describe rotations. For instance, represents a counterclockwise rotation of a vector v by an angle theta, or a rotation of CS by the same angle but in the opposite direction. Alibi and alias transformations are also known as active and passive transformations, respectively. Pre-multiplication or post-multiplication. The same point P can be represented either by a column vector V or a row vector W. Rotation matrices can either pre-multiply column vectors, or post-multiply row vectors. However, RV produces a rotation in the opposite direction with respect to WR. Throughout this article, rotations produced on column vectors are described by means of a pre-multiplication. To obtain exactly the same rotation, the row vector must be post-multiplied by the transpose of R. Right or left-handed coordinates the matrix, and the vector can be represented with respect to a right-handed or left-handed coordinates system. Throughout the article, we assumed a right-handed orientation, unless otherwise specified. Vectors or forms. The vector space has a dual space of linear forms, and the matrix can act on either vectors or forms.